Hi, and welcome to 7.04 Equilibrium Teaching Session. These are the Common Core standards that we're going to be applying in this lesson. The lesson objective is pretty simple. Explain the concept of dynamic equilibrium. Let's say you are on an electronic treadmill and you set that treadmill to go at 4 miles per hour. So you start walking, the treadmill's going backwards at 4 miles an hour. And let's say that you are not going 4 miles an hour. What if you go faster? What if you're walking 5 miles an hour? What's going to happen? What if you're walking slower than 4 miles an hour? Let's say that you thought you were going to have a lot of energy, but you just don't have enough energy. So you're walking at 3 miles an hour. And then let's think about what would happen if you were walking at 4 miles an hour and the treadmill was set to 4 miles an hour. So what would happen if you were walking faster than the treadmill was going backwards? So just imagine you're on the treadmill, you set the treadmill for 4 miles an hour, so it starts moving, but you're walking faster than that. What's going to happen to you? And if you said you're going to move forward, you are correct. In fact, you may actually hit the panel in front of you, right? You may walk right into it. So does this sound like something that would be at equilibrium? No, it is not equilibrium. If you walk slower than the treadmill, you will probably fall off, right? Because if you walk slower than the treadmill, then you're going to end up going backwards and you're probably going to fall off. Does that sound like equilibrium? Absolutely not. Let's say that you are walking forward at the same rate as the treadmill is going backward. You will stay in place. In fact, to somebody who's looking at you from a distance, you might look like you're not even moving at all. This is equilibrium. In a chemical reaction, the rate of the forward reaction equals the rate of the reverse reaction. Dynamic equilibrium is basically the same thing as equilibrium. The rate of the forward reaction equals the rate of the reverse reaction. A lot of times you'll hear it referred to as dynamic equilibrium. Sometimes you'll hear it referred to just as equilibrium. I have an example here. Hydrogen gas reacting with iodine gas to form 2 moles of hydrogen iodide. Now we can write this reaction separately. We can do hydrogen reacts with iodine to form hydrogen iodide, and then hydrogen iodide breaks down to form hydrogen and iodine. So when you look at this, we have the forward reaction and then we have this reverse reaction. And when they're both happening at the same time and at the same rate, that's where we get this double arrow from. You will notice in a lot of reactions that a lot do not reach equilibrium. Equilibrium is not something that every reaction will achieve. If it does, you will see the double arrow. If it does not achieve equilibrium, then you just see the one arrow. And you never see this backward arrow like this. I only did it for purposes to show you that we have a forward reaction and we have a reverse reaction. So at some point their rates are equal. When the rate of the forward reaction equals the rate of the reverse reaction, that is what we call equilibrium. Phase equilibrium is the same concept. It's just that the chemicals are only changing phases. They're going from liquid to gas. For an example here, we have liquid water, and it can reach an equilibrium with gaseous water. So let's say we have them in an Erlenmeyer flask, and we were to seal this flask. What you will find is that you will have vaporization of your water molecules. So liquid water will turn into gaseous water or water vapor, and that water vapor will condense and turn back into a liquid. And after this happens for a little while, we will find that the rate of the liquid turning into a gas and the gas turning into a liquid will be equal. And once those rates are equal, that's what we call equilibrium. And to the outside person, it may look like the reaction has stopped, but it really has not. The reactants are still becoming products, the products are still becoming the reactants. When we look at our graphs, we can clearly see equilibrium. In this first graph, if we were to plot time as a function of reaction time, the time that it takes. When we start, the rate of the reverse reaction is going to speed up. When we have our reaction, we start with a whole lot of reactants, right? We don't have a whole lot of products yet, so the time for our products to go back into reactants is pretty slow at first. As we make more and more products, we're going to have them breaking down faster and faster. And as we're making more products, our reactants are getting less and less, and so that time is slowing down. And eventually they will get to this magical time, the rate of the forward reaction equals the rate of the reverse reaction. And that reaction will just continue forever. Now how about down here? If we were to plot time and concentration, the green is going to be the reactants, the red is products. So let's say over time we start off with a lot of reactants, not a whole lot of products, and so our reactants, as soon as we start this reaction, they are reacting, so the concentration of them is decreasing while the products are increasing because we're now making them. And the products will keep going and the reactants will get less and less and less, and at some point we can see when we reach equilibrium because they don't change, and that is really important to realize about concentration. Once you hit equilibrium, the concentration does not change. Notice they are not equal. Okay, the reaction, the concentrations do not have to be equal, but they do remain constant. So once you reach equilibrium, the concentrations don't change because the rate of the forward reaction equals the rate of the reverse reaction. Two things important to remember. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and at equilibrium, the concentration of your chemicals does not change. They remain constant. With any system at equilibrium, we have what we call the law of mass action. Basically, we can just consider it the equilibrium constant. So the law of mass action basically states that at any reaction at a given temperature, we can relate the concentration of our products to the concentration of the reactants. Okay, so we can make a relationship between what they are. So what we do is we have our balanced equation. The W, X, Y, and Z represent the coefficients. Okay, the big numbers out front for balancing. A, B, C, and D represent our chemicals. And the way that we write our equilibrium constant is we call it K. And then on the top, remember what the brackets remember from Module 5. Remember the brackets represent molarity. So we're going to have the concentration and molarity of our first product, and we're going to raise it to the coefficient. So whatever the coefficient is going to be the superscript here. And then we're going to multiply that by the concentration of D raised to its coefficient, and then we're going to divide by the product of the concentration of A raised to its superscript and the concentration of B raised to its superscript. Notice that the products are on top and the reactants are on the bottom. You try it now. Write the equilibrium expression K for the following reaction. Welcome back. So following our example, we see that we have K, and we are going to put our products on top. Well, we only have one product, and that product is HI. I see that it has a coefficient of 2, so I'm going to raise it to the second power. And then on the bottom, I have the reactants, so that's going to be hydrogen. Hydrogen does not have a coefficient, so I don't have to put anything there. And I'm being multiplied by the concentration of iodine, and that does not have a coefficient, so I don't have to put anything as that superscript. That's the equilibrium constant. A system with an equilibrium constant greater than 1. Think about that for a second. If K right here is greater than 1, what has to be larger, my numerator or my denominator? So if K has a value greater than 1, it means that I have more products. That means my numerator is larger than my denominator. Just think back to fractions in your math classes. If this value out front here, if K is greater than 1, then our numerator has to be larger than our denominator. Well, what happens if the equilibrium constant is less than 1. So let's say this value of K was 0.5 or 0.01 or something like that. What would we expect more of in solution, products or reactants? And if you said reactants, you are correct. So if we have a value of K that is less than 1, you have more reactants in solution at equilibrium. And that means the forward reaction is not going to proceed very far. So when this reaction occurs, it's dominant left side. There's more reactants in solution. And that's just the way that the rates work. The rate of the forward is still equal to the rate in the reverse reaction, but we just ended up with more reactants at that point. Thank you so much, and have a great day.